All right. So I'll hand it off to Professor Shrikant Narayanan to give us a few opening remarks and kick us off.
Thank you so much, Krishna. Good morning, everyone, or wherever you are. Greetings. Good to see everyone at this third workshop, as Krishna pointed out, in the series of Understanding Media. So one of the things that we've been sort of collectively developing is this whole idea of computational media intelligence. By that, what we mean is that how can we illuminate media representations, portrayals, and perceptions, and their impact on people through a computational lens grounded in data, using multimodal interdisciplinary approaches, and through collaborative partnerships. I'd like to underscore these two words, interdisciplinary and collaborative partnerships. And this workshop today and the workshops that preceded this exemplify that, and the ones that are going to come forth that you'll hear later about. One particular focus of this has been, of this computational media intelligence, has been to support diversity, inclusion, and equity in media, both in terms of what we see and hear in media, but also understanding what impact it has on people. And to that, right, this set of researchers, the collaborative partners, have been, trying to figure out methodologies, experimental aspects, but also, working on developing scholarship that can support this. So it's a very exciting area, and we are hoping that this community will grow, and this workshop is part of that. And so I also want to contextualize this in a broader area. So over the last several years, some of the applications there have been focused on, for example, looking at how women are seen and heard in film and television, in other media forms. How can we sort of understand and relate it to what impact it has on society, and many other applications. Today's focus is on one specific theme or pillar in understanding context and environment that we see here, and and how that can sort of help us build these capabilities of media intelligence. So without further ado, I hand it over back to Krishna, who will exemplify this further. Welcome again, everyone.
Thanks, Sri. Thank you, Sri. I wanted to kind of give a real quick context to this context and environment in media workshop. And when we started talking about this broad area of computational media intelligence, we started identifying three broad themes or pillars of research. So our workshop, this is third in the series, as Sri mentioned, and our workshops were tailored around these broad themes. In August 2020, we started a workshop with identity and identification in media content understanding area. And then in April 2021, I believe, we had another workshop exploring interactions and relationships in media content. And finally, that brings us to this workshop, understanding context and environment. These are three broad themes we've been thinking about in terms of computational media intelligence and media understanding. And this workshop series has led to several interdisciplinary and collaborations with academia and Google research. All right. With that, let me quickly introduce our keynote speaker for the day, Dr. Makran Tapasvi. Dr. Makran Tapasvi completed his PhD at the Karlsruhe Institute of Technology in Germany, where he introduced several novel problems in the field of media understanding. Problems like movie Q&A, alignment of books with movies, and as well as summarizing and visualizing movie summaries. He worked as a postdoctoral fellow in the Willow Group in France, and in the machine learning group in University of Toronto, where he worked with several interesting problems related to movie understanding as well. Currently, Dr. Tapasvi is a researcher at Wadhwani AI Group in India, and we are very happy to have him as a keynote speaker today. Dr. Makran Tapasvi, welcome, and I will hand it off to you.
Thank you so much, Krishna. That was wonderful. Let me start sharing my screen, if that's okay.
Sounds good.
All right, so I guess it should be showing up.
Yep, we can see it.
Great, thanks a lot. This is exciting. Media understanding has pretty much been the focus of my research for the last decade now, almost. And it's really exciting to see so much progress made in this area, and probably what's going to come in the future, right? With large data and transformers now taking over much of our modeling efforts. So without further ado, let me start with just saying this. If you think of media understanding, one of the key things that is kind of considered here is the joint understanding of vision and language. And while common tasks for this include things like image captioning, where you're given an image and asked to generate a description of what that image shows, or video captioning, where you're given a short video clip and you want to describe what's happening in there, or maybe even a little more complex things like visual question answering, where the machine is shown an image, a question, and then is asked to answer this question. So in this particular case, given an image of Mona Lisa, you may think that this is kind of a cheating or ambiguous question, but then some of these things are often the kind of questions that we may want to eventually get our machines to understand. So I've mostly been working on story understanding in the field, and especially related to TV series and movies. And I would potentially define this as something like the ability of a machine to watch or read a story and perform some human-like tasks, let's say. So what are some of these tasks? Well, we are really good at searching and summarizing. So um, if you've watched Lord of the Rings several times, then maybe in this 10-hour extended edition of the movies, you know precisely, or at least fairly, what happens in which part of the storyline. And you're also able to summarize it or convey it in a different form to someone else. Humans are very good at answering questions about stories. Machines are not yet at least. We can use stories, and we in fact do use stories as a way to learn about human behavior, right? Much of growing up, let's say, it's not like you experience everything before kind of choosing a certain path to live your life. It's often like, hey, someone experienced this in a particular way, and therefore, if you also do this way, then, and this is the storytelling, you will probably do well or not do well. And accordingly, you're essentially learning from other people who have gone through such experiences. And we also want to try to mimic if machines are able to do this at some point. And of course, the big dream is maybe given a skeleton, something like the hero's journey, can we come up with stories, right? So I want to just also say that stories are, again, a very interactive form of vision and language coming together. My niece, who was 6 years old when I was writing my thesis dissertation, and I said, hey, can you draw me a little picture of what comes to your head if you're given a little description like this? So there's a dragon, fire-breathing dragon somewhere, and he's terrorizing a few villages. And this is what she came up with, right? And so you can clearly see it's a kid's illustration, nothing, not the next Picasso, but it pretty much captures what the text conveys. And this is kind of our innate ability of visualizing or creating a mental picture of sorts of things that you see or read about if it's related to storylines. So you have both instances of villagers also going back and asking help from their queen. The other thing is we all love stories. I think there was this really nice video in a talk by Antonio Torralba from MIT, where you can see the experience that this kid has. And so let me try to play with this video. My audio may be a little weak, so you may need to increase your volume. Right. So essentially, the mom is reading out the story to the kid, and then the moment the book closes or the end is uttered, the baby starts crying, and this repeats on and on and on. And this really kind of shows, even as 2-year-olds or just even now, right? You take away Netflix at the point of a very exciting cliffhanger. You might not cry, but pretty much experiencing emotions that the baby is right now. So in our previous work, we had done some work on aligning these TV episodes with plot synopsis. This was kind of trying to combine different modalities together. And so from Wikipedia, you have these plot synopsis, short sentence descriptions of what's the kind of key events or summary of a storyline. And you could see the video, also see what the main characters are doing, and you could try and align these components. So in this particular case, you can see that two people are trying to scan books into a computer. So we worked on trying to align these texts, and were able to do so fairly well, not accurately, but fairly well enough to be able to use these sentences perhaps as very descriptive and nice captions, but also perform some searching and searching through the storyline, because you could now convert this problem of searching through a video or a plot of a video by searching through the text of the plot synopsis and using standard tools there. And then you had this alignment in between, which allowed you to jump to the right part of the video. And of course, you could do this with short texts like plot synopsis, but then you could also do this with longer texts like books. And in this case, Game of Thrones had just released at that point. So there was this clip where Arya is folding her clothes. And this is really well described in the book. So you can see that she's in the room packing some chest. And of course, maybe you don't see that it's a tiny wood chest, but hey, you get the kind of overall plot synopsis, right? And you have the characters, the actions, the dog in this case, a pet that is helping, and then maybe even very descriptive context of what's happening in this scene, right? So moving on from this, we were wondering, can we think of understanding human behavior? And well, it kind of goes into the gray area slightly of how do you collect data of human behavior? You could probably surveil everyone, but that's probably not the right thing to do. So you could either do this, like they did in the Batman movie. We didn't have access to machines like this. So we went and said, let's use movies, right? Because at least the more real life, non-fantasy movies often tend to have scenarios that one may experience in their real lives. And this could include things like bullying, rescue scenes, speeches at a wedding, or potentially signing contracts, right? When you're joining a new firm. So how do we go about this? I want to present two kind of works in this direction. One is about reasoning on storylines, and then in particular, we'll look at character interactions and relationships and how they combine and help each other. So let's start with the first one. In this case, a kind of early motivation was if you want to be able to do story level question answering. So in the case of The Matrix, for example, you may want to answer questions such as why does Cypher betray Morpheus? Or what does Neo find at the source? And these are complicated questions, right? So even if you watch the movie once, maybe you have not got it, or there's a chance you may need to go back and watch it again. And this is not only complicated because it's a 2-hour movie and video processing is hard and not there yet and features are not solved, but it's also hard because what you're really trying to get at is what is the mental state of this person while doing the actions or doing the things that he or she did, which is complicated. So again, you have long movies, you have complicated dependencies across the entire multiple scenes, and then different interactions and emotions and intent may come into play. And if you truly want to understand a movie, then you probably want to try and understand each of these aspects in a more clear way. And this is what really led us to this idea of creating short graphs for movie clips. And so towards understanding human behavior, we were thinking of, all right, sorry. So kind of our goal is to have this, if you've seen the movie Big Hero 6, then there's this really good robot which helps this kid, and we can kind of see this case as an example.
Your body temperature is still low. Yeah.
Right. So, I mean, the goal is to hopefully build some good robots, right? Where they're able to understand this particular workshop's domain, the context and the environment, and how people are feeling, and act accordingly, and provide warmth in this case because the kid just had come up from some getting wet in the water or something. So towards this goal, you need to understand the people, and so we were thinking of, okay, let's take this whole movie and break it down into individual scenes. And then toward understanding each scene, let's create these small situation graphs which try to capture much of the happening or the story-related events that take place in this short 45-second to 1 minute long video. And so this is mostly going towards how do we get this data manually right now. And then you can also potentially think of ways for machines to be able to look at any movie or any movie scene and generate such a graph. So what are some of the main aspects of human behavior that we try to capture? One was situations. So these can be thought of as overarching themes that result in scene breaks in a typical movie. So you can have things like a wedding scene or a particular phone call or something like that. We had interactions, both verbal as well as visual. So you have a lot of talking in movies, especially in things like drama, asking, explaining, ordering, and so on. Then, of course, and some visual interactions such as kisses or hugs. Through these interactions, one may imagine, or as an audience, you do end up drawing relationships between people. And it's not often always explicitly told, but seeing the age difference, for example, you may judge that probably the woman is the mother and this child is probably the son or the daughter of the mother. So you could have family relationships, but you could also have non-blood relationships like strangers or colleagues or neighbors, right? And finally, we had this long list of attributes, including things like physical characteristics, adult female, to a whole range of emotional attributes, including, and not just like the classic 6 emotions, but just going beyond what typical words are used to describe people. And so what we did was we asked annotators to look at a clip and then try to annotate some of these. They were given the freedom to choose any additional word if they want. So there was an initial seed vocabulary, but then they also had the freedom to add new words, which really allowed them to express themselves in a better way. So what is the graph? Let's look at this short clip from Forrest Gump. Right, so you kind of see a classic scene. You might say that the situation is one of bullying, and okay, so you can say that the situation is bullying, and you can also create some more additional labels that might help, especially computer vision systems, where you might want to tell them where is this happening, because often the scene is correlated with the situation that's taking place. You can have a short description, just a natural language description of 2 or 3 sentences about what's happening, and note that much of this always focuses on the characters, because those are the things, or those are the entities that are really experiencing much of these emotional turmoil, let's say. So you start with characters. That's kind of the natural place to start for understanding any story. And so we also decided, let's go by creating nodes that represent the characters as the first step. And then you can add attributes, physical as well as emotional. Over here, I'm only showing emotional ones. And in this case, you can see that Forrest is scared, the bullies are kind of violent, and then Jenny, the girl asking him to run away, is kind of compassionate. You can also kind of then capture the interactions that are taking place between these characters. So in this case, bullies hit Forrest, and then be a bit more descriptive by saying, how do they hit him? Well, with rocks. They also insult him, that he's a dummy. And then why do they insult him? Potentially because he's different from them. So there's sense of reasoning involved, as understood by a narrator, for example, in this case. And based on these two interactions, or based on a bunch of other interactions, one may kind of create this relationship of enmity between bullies and Forrest. Then we can see that Jenny encourages Forrest to run away from them, and then Forrest runs away from the bullies. And because these graphs are directed, you're able to capture the interaction as A does something to B versus B does something to A, because it's not exactly the same. And the final thing we add on to these graphs, just to provide a bit more grounding, as is common in vision and language, to bring together what part of the video, in this case, corresponds to some of these interactions. We add a little timestamp node which says, okay, hit mostly happens from the first 13 seconds, and runs away happens typically in the last half of this video clip. So you have this rich graph now for each scene in a movie, and if we had this for about 50 movies, total of 7,600-ish graphs. And if you just kind of aggregate information across all of these, right, you kind of, a social common sense of sorts emerges on its own, which is kind of surprising for us. We didn't aim for this, but it just happened. And so you can see things like at a party. So what I'm showing is a heat map of situations versus interactions. You have cases where at a party people dance with each other, or at a robbery people are threatening or yelling at each other. And at a wedding, there's bias of movies, of course. Hopefully the couple agrees in this case, right? And the relationships and emotions are also very interesting. So parents in movies are loving, while lovers are actually upset, more than loving at least. So it kind of captures, obviously, the biases that we portray in a movie. And thereby you may want to be cautious, I guess, about how much of this should be directly learned by machines. But you still get a sense of how people are interacting and behaving with each other. Some other things you could do, because we have these annotations across the entire movie almost, is you could create a flow graph. So take any node, take any starting point. In this case, if it's a date scene, then create a bunch of all options that follow the date scene. And in this case, I'm picking the scene of intimacy, followed by waking up, and followed by breakfast. So you're kind of creating a timeline of sorts across what the characters may have experienced. And because you have this graph now, you can think of this as a way to generate new movies and say, I can start at any point, sample, give some probabilities potentially, and you'll be able to create relatively meaningful situations, at least if you take like 5 or 10 at best. When you extend this to too many, then yeah, probably the story is not going to be the best one. But this is kind of a first step towards being able to make sense of 10-minute videos, and as well as creating something coherent in that direction. You can also do a lot of modeling with movie graphs. One of the things that we did was this graph-based clip retrieval, where the idea is you're given some kind of query, which is not in a typical textual query, but a graph-based query. And in this case, you're told what the situation in the scene is, and then you're told that there are two characters, both are adults, male and female, and that they're regretful and confused. You could add other interactions and relationships as a way to filter them, or you could remove some of these annotations, and then you'll get potentially more variety of options. In this case, we're able to find 2 clips. One is from the firm, and the second one is from 4 Weddings and a Funeral. And you can see that, so this one is the correct one from which we got the partial graph. And this one is kind of very relevant to the storyline, and you can see at least two people talking with each other, and they clearly don't look happy, probably regretful. It's not a judge, so they do get that wrong, but kind of work in progress, you know. Right. So the other thing you could do, because we have these reason annotations, as said before, you could imagine that you have two characters, some more details about them. In this case, we learn, or the model also learns, that they are spouse with each other, and at a house, they're talking about adoption. And then the interaction is that they embrace. And so then you can ask the model, why does this happen? And so the model itself is not very complicated. You have an encoder-decoder kind of architecture where you're taking in all this information, and then we had an LSTM at that point, which was trying to generate the reason. And of course, this is, I mean, you could generate multiple reasons why this may be happening. You probably don't have a single correct answer. And in this case, they're able to, so the model is able to say something like, the man is scared, which is kind of a very plausible answer. Adoption is serious business. And if you watch the movie clip roll out, then actually it's that they're glad that they'll have a baby. So given this information alone, you're able to generate some form of diverse opinions, and potentially if you add emotions like happy or sad or something, or tense, they may be able to get these more correct as what the ground truth says. So first step kind of at really trying to understand why people are doing what they're doing. And the third thing was interaction ordering. So you kind of forget everything else in the graph, and you're given these two characters and their interactions. And assume if you have like a set of interactions, can you order them in a way that it kind of makes the story kind of coherent? So it's unlikely that Forrest runs from the bullies before they hit him with rocks or insult him. And so we provide again through an encoder-decoder model where we try to estimate which of these interactions occurred first and which later. So you're kind of trying to learn some causality of sorts through the storyline and through how the movie has evolved by watching just these small graphs and these inputs and abstracting away all the complexity of the visual domain. And so, yeah, in this case, this was like a successful example where it worked. There were many ones which were, again, ambiguous in the sense that there was not always one correct answer. Right, so this was kind of mostly about reasoning about stories and using the movie graphs. We had a follow-up work on this, on joint understanding of interactions and relationships between characters. And this was mostly motivated by the fact that often social relationships are driven by the kind of interactions that take place between characters or people in reality. And so if you laugh and spend time with someone, you're probably likely to be friends at some point of time. Or there are also the other way, like relationship-driven interactions where there is a designated teacher in this case who is probably asking questions or teaching or even consoling the students. So there is kind of a directed nature of, or joint nature of interactions and relationships. We wanted to explore if we can help or get a model to learn both simultaneously and potentially improve performance for both. So we came up with this multimodal embedding, which looked at the clip, the text, the dialogue. The details on how is probably not as relevant. And what was important was also to have like a visual box or a region of interest for individual characters. Because remember that our interactions in particular and even relationships are directed. So if you want to understand what is character one doing to character two, you may want to exactly know who is character one and who is character two. And so we had this final representation which combined these four pieces of information. And if you look at some interaction prediction with these modalities, so if you have only the visual domain, model in this case, so I'm showing you a couple frames for a proxy for a video, the model predicts with a fairly high confidence that these people are walking away from each other, or in particular, I guess this person is walking away from this one. But if you add the textual domain, and in this particular case, the textual domain has no dialogue, so you just have a vector of all zeros. And it was the most curious of things where the model was then saying, hey, it's probably the interaction is leaves. And this is really cool, right? Because the model has figured out that if A walks away from B, maybe they'll at least say bye. But then if they walk away without any dialogue, maybe there's kind of some fight before that happened, and now the person is leaving actually. Of course, then if you look at the individual tracks and highlight them a little more, then in this particular example, the model is able to come up with the correct interaction. Right, so how was this done? You have this interaction classifier, you had a separate relationship classifier which looked at multiple clips, because one assumes that relationships may not change so quickly in a typical movie. And we just had a little adjustment where you would feed both the relationship feature representation and the interaction representation, and then train both simultaneously to predict it. And we tried a bunch of other combinations. This seemed to work best for a particular set of data, at least. So what's interesting is you get these really tiny boosts in performance. But if you look at the details, you'll see that interactions which are particular to certain relationships see a large improvement in performance. So something like hugs or introduces, you see like tremendous 17-14% of accuracy improvement, while interactions which basically occur between all relationships, the model is not able to make any sense of what this new information of the relationship is, and therefore it kind of drops in performance. We tried a bunch of things to not let it drop and just at least hold it to constant, but didn't seem to work out. And the same thing can be also seen for relationships. So again, relationships which are driven by relatively unique interactions, see a big bump in performance, while the other ones, like mostly related to talking, everyone talks with each other in a movie, saw a drop in performance. The other thing we tried to do was also explain which pair of characters are involved, and this is a little involved. So given a clip, essentially we are saying we don't know which are the pair of characters, we don't know the interaction, we don't know the relationship. Let's try and model a tensor which kind of captures all of this, and both at training and evaluation time. So we treat character pair between which all this interesting stuff is happening as a latent variable, and then you want to kind of try it for all pairs in your particular clip. And some training details about using max margin loss with negative sampling and so on. But essentially, at inference time, you had this 3D cube of sorts where you had all relationships across all interactions across all pairs of characters that you may see in this particular clip. And then you could slice this in different ways. So given two things, you could try to predict the third, or given nothing, you could just pick the argmax of sorts across this whole tensor, and thereby find who's doing, or which pair of characters, what are they interacting, and what is their relationship. And of course, this is very hard. Generally, all these predictions are hard, and this is in particular very hard. And so, but we still found a clip where actually it got everything right, which was kind of nice. And so I'll show this example here. You have three people talking at the dinner table, and so there's a bunch of dialogue there. You have combinations of track pairs where there's a couple friends, there's a parent and child, and then there's a child and friend of the parent, who in this case is annotated as a stranger. So it could be given two options, and you could be asked to predict the third. So in this case, asked to predict the pair of characters, and this is it's able to get this right in this case. You could be given the other two options, in this case, character pair and the relationship, and you could ask what are they doing, so predict the interaction. Or the third option, and you could try to predict the relationship. And then finally, you could be given nothing, and you want to make a prediction about everything. And so this worked partially. I think the accuracy of this was like a meager 2% or something. But this is really a hard problem, as you may imagine, because you need to get everything right. And of course, it's not too much data. It's just 50 movies or even 35 or so that you actually use for training. Kind of still nice that the model is able to learn some of these aspects, though. So yeah, with that, I just want to put in a message there saying social situations can be tricky. I think this was a really nice cartoon that captured it. Depending on where you are, the context and the environment, you may want to be careful about what you say. And eventually probably be careful about what your machines are saying, right? And yeah, thanks to all my collaborators and students. This was kind of fun to do. You get to watch movies and college research. It's always fun. And with that, I'll stop here for questions. Thank you, everyone.
Thanks, Makaran. Let's unmute and give Makran a round of applause.
Thank you.
With that, let's open up for some questions. Feel free to use the raise your hand feature on GBC, or just add your question on the chat. Okay, Shri.
I'll start. So Makran, thank you so much. Very, very impressive work. And one of the things that I would love to hear your insights, right? Some of the more linguistic descriptions that you have about people, places, their states, and so on, right, gets very complex very quickly, especially in a very rich data that like a movie where or story that we're trying to describe. So what were some of the lessons learned, like even trying to devise a taxonomy that or a guidelines that you gave your annotators that did the task, which if you would mind.
Yeah, sure. Yeah, that's a great question. I think we probably spent like 2 or 3 months trying to come up with something, and then realized it really is never going to capture everything. And then towards the end of the project, after we had like 30 or 40 movies annotated, we had this 14-page booklet to give to our annotators to say, hey, this is how you should annotate, right? And that's kind of overwhelming, because typically in an AMT like task, you'll have draw a box here by looking here, and there's 3 bullet points and you're done. So yeah, the set of different sets of information came from different places. For relationships, we kind of asked AMT actually to come up with a bunch of relationships that they often see in movies. That was a kind of initial seed set of vocabulary. Interactions came from The Sims. So we took a lot of information from games, video games that use kind of aspects of social interaction, or just having characters do their thing. And so initial vocabularies for those came from that. Again, as I said before, the annotators were free to add their own new things, which also helped to some extent. Now, this does raise the difficult question of, if you have pre-formed text in a certain way, how do you evaluate when the graph is created whether that's good or not, right? And so yeah, this is hard. I don't think our translation metrics or the captioning metrics, typical natural language comparing two strings, evaluation metrics are there yet to make sense of things. But maybe at some point of time when that happens, it'll be good enough. Currently, which is why retrieval made more sense than generation, because there was a more formal way of evaluating things.
Thank you.
Makran, I have a question. Oh,
yeah.
No, Rona, go for it.
Hi. It was a very interesting talk. Thanks, really.
Thank you.
I have a question about the theme of the movies that you chose. For example, each movie it's a movie because it's about a particular story, a particular scenario, or a theme, or it either explores a drama or a comedy or a fiction. So when you combine all of these movies together, and given that each of them have very different level of interaction, stories, and relationships going on, how do you train them together?
Right. Yeah. Wonderful question. I think the key thing that we kept in our head was we don't want to go too much sci-fi. Pretty much everything that was non-sci-fi was within the realm of potentially experienced in real life by some people at least. And so that was kind of the main choice. Now we did not actually have like separate, like we wanted to get 10 movies in comedy or 10 movies in romance and 10 in historical fiction or something. So we went with generally what seemed to be popular and available at some point of time. And mostly they typically covered normal human movies, right? Drama, romance, some history stuff, but yeah, mostly that. The other interesting thing that we did was, if you look at some of these graphs and chain them together, and then do clustering across these graphs. Or so instead of comparing similarity between the video and the graph query, you could compare similarity between two graphs from two different movies. And it was really cool to see that the model is, or just comparing similarity and doing some form of clustering led to genre-specific movies coming together, because the situations or the emotions experienced by some of these characters is kind of similar. So I think the classic example was, we had The Flight, the movie which involves a plane crash, and we had Titanic, ship crash. So, and both of these were like really high scoring in similarity, which seems to indicate that there's something meaningful going on behind the story.
All right. I have a question, Makaran. I know you said generation is much harder than retrieval, but do you have thoughts on summarizing these complex stories as graphs rather than natural language descriptions? One and two, and then have you thought about, like, when does this graph structure break down to create unrealistic stories? How far you can push, say, the context information or the identity information?
Right. Yeah, I don't think we really thought much about when it would break down. We did think a lot about why is a graph better than a description, and fairly convinced at that point, at least, that descriptions are more easy to interface with, I guess, but they're so diverse, and you can just approach the same clip of even 1 minute in so many different directions, that having any form of agreement, let's say, between people is going to be very hard. That was one. And the other thing was, graphs provided a very discrete way of analyzing the information presented in the video. Now, given that, but given the progress that we have seen through GPT models and so on, I don't know. Maybe it's different now, and maybe we are ready for a point where you feed in a video and can generate some of these descriptions. So this is something we would really want to try in the future, where you give it a 1 minute video, can it generate these 2 or 3 sentence clips that descriptions that we have as part of the annotations, while being limited with just 50 movies, right? So there's not much data to lean on. But yeah, this is something to think about.
Thanks, Makaran.
Thank you.
We have about 30 seconds. Any more questions or points of discussion? All right. If no more questions, let's thank our speaker again. Thanks, Makaran.
Thank you.
And we will resume in, sorry, right. We'll resume in 5 minutes. And we have an exciting series of speakers in the lightning talks in the next session. So I hope to see you all in 5 minutes at 10:50 a.m. Pacific time. Let's wait for a few minutes while everyone is getting their coffee or water. Let's wait for a few more seconds and then we can start. All right. Welcome back again. Welcome back again. And we have two sections of lightning talks. And the format for lightning talks will be as follows. So we have 3 speakers in each of these sections. And the speakers, each of them will present for about 10 minutes. And please hold your questions until the end of all the speakers finish talking within a session. So at the end of all three speakers, we can have a Q&A and discussion section about the topics they presented on. All right. With that, the first series of lightning talks, we have 3 speakers, right? And as Jen has reminded us, feel free to drop your questions also in the chat. If you prefer that, just make sure you point out which speaker your question is referring to. And our first series of talks are by Morgan Shorman, Amy Harris, and Kamal Singh. May I ask the speakers to briefly introduce themselves before they present? Also, to keep the flow smooth, I'll be changing the slides. So just indicate to me when to advance the slides. All right. With that, our first speaker is Morgan. Morgan.
Yo, thank you so much. Hi, I am Morgan Klaus Scheuermann. I am currently a PhD student at the University of Colorado Boulder. I am in information science there, and I study primarily how identity and values are embedded into computer vision. So this talk is going to be kind of high level, a little bit less focused on media and a little bit more focused on computer vision and how data values in computer vision as a discipline shape the outcomes of computer vision. And so there will be a large focus on context. Sorry, the slides are a little bit messed up, I think, because I made them in PowerPoint and then imported them, and it looks like they're a little messed up, but that's fine. So I'm going to be presenting this work, Do Datasets Have Politics? Disciplinary Values in Computer Vision Dataset Development. This work was published at CSCW this year and was awarded a Best Paper Award. I did this work when I was interning with the Ethical AI team at Google Research, and so also want to introduce my collaborators, Emily Denton and Alex Hanna, who worked on this as well. Okay, so advanced slide. So data powers modern machine learning. Computer vision is a subfield of machine learning focused on analyzing and extracting information from images and videos to make predictions, as we just saw in the last talk. Given the centrality of data sets to computer vision practices, the data sets underpinning modern computer vision algorithms have come under increased scrutiny in recent years, raising concerns regarding the image contents and categorical structures, as well as the methods of construction, documentation, and maintenance. Advanced slide. Audits of computer vision data sets have uncovered serious concerns about representation of different sociodemographic groups. For example, Bolomwini and Gebru found that darker skinned women tend to be misclassified more often in large commercial systems, indicating an underrepresentation in the data. Advanced slide. Stemming in part from the lack of transparency of many of these data sets, several documentation frameworks have also been proposed in recent years, such as data sheets, data statements, data set nutrition labels, and data set requirement documents. Advance slide. Finally, the categories structuring computer vision data sets have been increasingly critiqued. In a lot of my own prior work, I've discussed how data sets where race and gender categories are used portray these classifications as natural and immutable. But largely, research on computer vision data has not focused on the underlying values of their creation, documentation, and dissemination. Advanced slide. Our work focuses on examining current dataset documentation practices and the values structuring dataset development within the field of computer vision. After all, as Langdon Winner famously wrote, artifacts have politics, and scientific disciplines themselves are in culture with their own specific practices and values. Riffing off Foucault, who defined knowledge as a practice imbued with discursive power, in which a scientific truth is constructed through classificatory practices. Next slide. Given the necessity of data to modern computer vision, this work focuses specifically on examining the underlying values of computer vision data sets, the practices of collecting, classifying, and disseminating data to be used in building and evaluating computer vision models. In this work, we were driven by 3 research questions. The first, what do authors document about the dataset curation process? Advanced slide. The second, how do authors document the dataset curation process? What language do they use when they're describing the process, the dataset itself, and the value it pertains to their audience? Advanced slide. And third, what do answers to these 2 questions communicate about the values of computer vision datasets, and what values are not being communicated as a result? Advanced slide. To answer these questions, we analyzed documentation from 113 different computer vision data sets across a variety of computer vision related tasks. This included tasks that were based on the human faces, tasks that were more based on full body, and also non-corporeal tasks that included things like object recognition. For this, we built an extensive codebook. We make this available in our paper, which I can also link in the chat, and it's also at the end of this slideshow. Advanced slide. In the paper, we present findings in 3 themes focused on different levels of the dataset curation process. So first, we present findings on the disciplinary specific practices of dataset authors. For example, how data is generally viewed as crucial to scientific progress in the field of computer vision. Advanced slide. Second, we present findings on data instances and what makes certain data sought after for computer vision data sets. For example, authors often sought data that was portrayed as objective or was also large in scale. Next slide. And third, we present findings on the human actors involved in the data process. So this included not only the authors, but also the annotators and the data subjects, and how dataset authors discuss these roles. For example, human appearances and behaviors make consistent data challenging to collect. So things like having various different types of clothes, for example, can be difficult to collect and annotate. So next slide. Through an analysis of these findings, we characterize the values of computer vision data sets by discussing them as trade-offs to otherwise silenced values that sit in opposition to those communicated through the documentation processes. Next slide. We detail 4 value tensions. So dataset authors generally valued efficiency over care, universality versus contextuality, impartiality over positionality, and model work over data work. Next slide. So we identified how authors prioritized efficiency. For example, being able to cheaply and quickly annotate large amounts of data over care, valuing slow and thoughtful decision-making processes. In the paper, we make recommendations for instead flipping these values. So if we were to value care over efficiency, that might include collecting data with special attention to the privacy and ownership rights of those data, compensating data subjects for their data and annotators for their labor, and storing and safeguarding data sets with proper data stewardship protocols in place. So these were things that we generally did not see in these data sets. Next slide. They also value the concept of universality. So the idea that every object in the world could be captured into singular data sets, having very large generalizable data sets, over contextuality, that data should be situated and shaped by specific time and task. So if we wanted to incorporate contextuality instead of universality, we could see designing data sets for specific temporal, geographic, community context rather than generalized use, and even conducting empirical studies to understand the context of intended use before designing the data set, which generally we actually didn't see in any of these data sets. Next slide. Authors have valued impartiality in terms of both data collectors and annotators introducing no human biases over positionality. For example, collecting a data set for something like medical classification might actually benefit from the expertise of medical professionals being involved in that process. So incorporating positionality might include positionality statements that dataset authors make to incorporate reflexive thinking about who they are and how that is shaping the data set. Reporting author and annotator demographics might be a useful tool for making transparent how decisions might be made during the data process, and actively engaging with potential social and political implications of the data within the context of the culture that it's being deployed in. Next slide. And finally, model work was valued over data work, meaning authors spent most of their documentation space, particularly when those papers were published in archival venues, on explaining modeling decisions and behaviors, while rarely explaining data practices. So we often saw only maybe one paragraph or two paragraphs dedicated to the data itself. So incorporating data work over model work might include assigning data sets a stable DOI. This isn't something we saw very often. Creating a data maintenance plan in order for the data to remain relevant and useful. A lot of data sets wind up moving around on personal websites or just you can no longer find them, even though they might still be in use somewhere. And publishing rigorous and detailed data set documentation. So this might include some of the prior work that I referenced, which is like data sheets for data sets and things like that. Next slide. So data sets as artifacts are imbued with their own specific politics. The values explicit in computer vision data sets often ignored or implicitly critiqued values of human-centered computing approaches. So we argue that if we're going to have data sets and computer vision technology relying on those data sets that honor human-centered values, then we have to engage in careful, contextual, and position-aware data practices. Next slide. So thank you for listening to this. There's a link to the paper here, and I can also put a link in the chat. And I'm happy to take questions after the rest of the speakers.
Thanks, Morgan. It was a great talk. Let's hold the questions for after the speakers of the session. Our next speaker for the lightning talk is Amy Harris. Amy, on to you.
Hello, thanks so much. Can you hear me okay? Great. Okay. So hi, thank you so much for everybody here. My name's Amy Harris. I'm a second year PhD student in communication at Simon Fraser University in Vancouver, and also working for Wendy Chan at the Digital Democracies Institute, who suggested me for this talk. So thank you to Wendy. Today I'm going to be sharing some of my work in progress, hopefully giving you some things to consider, and I'll be super interested to hear any feedback or comments. So next slide. When I was preparing for this talk and looking at some of the other abstracts, I wasn't really sure how my area of research kind of fits in, as I'm not really working with computational data. But in thinking about the themes and methods and the overall aim of media understanding, I hope that mine offers somewhat different but still relevant concepts to the workshop. So on this slide is just some of the concepts that form the main focus of my work, just to give you an idea of what I'm going to be discussing. So to give some context, next slide. One of the key barriers that's prevented people really understanding the impacts of human activity on climate change is because it is such an abstract concept involving invisible gases in the atmosphere. James Hansen, who's a NASA climatologist and former advisor to the US Senate, in an article in 2012 with a couple of colleagues, described that the greatest barrier to public recognition of human-made climate change is probably the natural variability of local climate. How can a person discern long-term climate change given the notorious variability of local weather and climate from day to day and year to year? He and his co-authors acknowledge that the way that most people therefore understand climate change is through local weather changes, but find that hard to connect that with their own actions. In using media to try and convey that connection, there's numerous examples of people attempting to convey climate change in contexts that people do understand, and I'll describe some of them here. Next slide, please. So one person who saw technology as a solution to connecting people with the impacts of climate change is James Balog, and you may have heard of him or seen footage of his extreme ice survey project, either through the project itself or in the documentary Chasing Ice. He describes the project on their website as an innovative, long-term photography program that integrates art and science to give a visual voice to the planet's changing ecosystems. And he and his team placed cameras at specific sites around the world to take still pictures on timers, which are then combined into time-lapse videos which show the recession of glaciers. The aim is to convey the impacts of climate change on a scale that cannot be appreciated in real time. Next slide, please. Another really interesting project I heard about a few years ago is the use of virtual reality games and climate change, the Lost City of Mur being one of them. This was a game that has been sponsored by the UN and has won many awards for innovation. It involves a virtual journey to save a coral reef, and through connection with a smartphone app is intended to connect the imagined realities of a coral reef in danger with the actual actions you take, comparing things like the way you travel, and the player wins awards for choosing to walk or take a bus. And things like that. This connection with real-world action has been one of the technological innovations that seems to have potential for connecting our bodies with real actions. Next slide, please. Art also offers many entry points into opportunities for connecting people with climate change. There's probably lots of examples that you can think of, but here I just chose this image, which was used in the David Wallace Wells article on the uninhabitable Earth. The article itself was a bleak projection of reality, and the accompanying artwork, unlike many news articles that use kind of real-world images of flooding or heat waves, for example, this used a number of constructions from Heartless Machine, which the artist calls modern fossils. These are kind of artifacts that are encased in concrete. This particular example of the air conditioner particularly resonates as the article refers to the rising temperatures we'll be experiencing. Next slide, please. A more empirical method of trying to convey the impacts of climate change has been through charts and graphs. Michael E. Mann's hockey stick graph is probably the most famous, but I included this one here, which was seen this week in commentary about what was going on at the COP26 conference. This graph changed as you scrolled, showing what the results of no changes would be to the amount of land exposed to wildfires annually. James Hansen, that I referred to earlier, also used a number of graphs in his article. And these charts can be incredibly helpful for seeing data in a useful way, but are limited in how much they can convey effectively about what has happened and what's predicted to happen. Wendy Chun, who probably you're all very familiar with, in an article in Critical Inquiry in 2015, which was called On Hypo-Real Models of Global Climate Change, a Challenge for the Humanities, talks about the efficacy of climate change modeling and how it relies on data from the past to predict the future. Unlike some modeling data which is used to show what will happen, Chun describes global models of climate change as showing and predicting what we don't want to happen in order to try and enact change and to stop those effects. However, again, the limitations of graphs and charts for only some informed people is not wholly effective in this endeavor, and I'll come back to that slightly later. Next slide, please. So technology's role in how we understand our relationship with the world is one that's a key concept for my work. And Peter Paul Verbeek's technological mediation theory is really helpful. His theory describes that technology helps us to shape the relations between human beings and the world, seeing technological artifacts as mediators between human-world relations, as being part of the relationship, not necessarily removed or separate from it. Linked to this is the concept of phenomenology, or how meaning is constructed from our experiences of things. And Don Idey's post-phenomenology tries to account for how new smart technology has created artifacts that go beyond just being things, that include relationships with us, raising interesting questions of subjectivity and agency. In practice, this means that the technology that we use impacts the way that we see the world and potentially changes our reaction to it. It challenges the arbitrary divide that is often understood as being between humans and the technologies and the tools that we use. For example, for the extreme eye survey to be effective, we look through the images the camera produces to the film and are moved by them without thinking about the camera or the technology that produced the image itself. However, where technology fails in some ways in the examples above is in inspiring that action. The aim of the images in the EIS, the virtual reality game, the art accompanying the Wallace Wells article, and the plethora of charts used relies on the premise that seeing is believing. That was the overriding impetus for Balog's Glacier project. But clearly, seeing might be believing, but is not enough to link that to tangible actions that people take daily contributing to climate change. Where they fail, according to Margaret Grebowicz, is that in trying to make real for people who do not have direct access to them, the representations actually create a greater barrier. Drawing from Guy Debord's theory on the nature of spectacle and questioning concepts of authenticity, what Grebowicz claims projects like the EIS do is still perpetuating the abstraction of climate change. In the time-lapse videos, what we see is the effects of climate change, which actually happens in the gaps between the shots. Slavoj Žižek theorizes that when we try to show the real in ways like this, it's actually impossible because it creates a spectacle. It becomes immersed in ideology and the symbolic and the imaginary, drawing from Lacan. In short, it all becomes too remote and intangible. So what does really bring these sorts of concepts into reality? How can we truly connect the impacts of climate change with our actions in order to inspire changes? Next slide, please. So one way is through embodiment, because embodied experiences are often understood as being much more formative and constructive. In the same article from Wendy that I referred to earlier about the challenge that climate change models have in convincing people about climate change, she ends the article with saying that I am willing to wager that the debate over global climate change will be over soon, not because people believe models or means, but because proxies, such as weird global events, will convince the majority of its existence. This year, events in British Columbia have had increasingly direct physical impact. The heat dome in June meant that the highest temperature ever recorded in Canada broke records for 3 days straight in a tiny town called Lytton, where it reached 49 degrees centigrade or 121 degrees Fahrenheit. Just hours after the high temperature was recorded, the town was burned down almost completely from wildfire. So within the space of a couple of days, it broke the heat record and then was destroyed. If you're anywhere affected by things like the heat dome or similar intense heat waves, unseasonably high temperatures, unseasonably high rainfall, or smoke from wildfires, you will have felt those impacts in your body from having to adapt your behavior. It's likely much easier to recall what smoke smelled like, how hard it was to do anything in the heat, than to recall what seeing a photograph did. So as we all accept that technology is ubiquitous in our relationship with the world, how can we kind of use that technology and how can it help to capture these embodied experiences? Next slide, please. One area that certainly has potential is in the use of wearable technology. Devices such as those seen on the screen are currently used in healthcare to promote and ostensibly increase our senses of well-being. And I'm not going to get into here whether that is exactly what they do or not, or explore many of the problematics that come from wearable technology, the use of computational data, for example. You guys are very much more experts in that than I am. But in connecting our physical bodies with the world using this technology in a similar way to how the VR game Lost City of Mir connects the game with your actions in real life, developing ways to demonstrate and connect people with their actions and the embodied experience in one I'm keen to explore. Next slide, please. So as I said, these things are kind of questions that I have and work that I'm going to be looking into. My master's research looked into how smartphone technology impacts our risk perception when we go hiking. So the interaction of outdoor activities with technology is likely going to feature in my research. Questions on the screen show where I'm looking to explore. So how have the events of this year impacted people's connection to climate change? How does wearable technology impact our relationship with the environment? Where are there opportunities to use technology to connect with our environments? And lastly, and possibly most importantly, how can we ensure that sustainability features in future design? Thank you.
Thanks, Amy, for that fascinating perspective. Our next speaker in this series is Komal Singh. Komal, on to you.
Hey everyone, thanks Krishna. My name is Komal Singh. I work as a program manager at Google, currently working in the research product area. I'm also an author by accident and also a mom of 2 kids, which is by choice, not by accident. So today I'm going to talk about Story. It's a 20% project that I lead at Google, and we're a bunch of people from various disciplines. There are a few software engineers on the team, a few people from D&I, diversity and inclusion, a few people who are early childhood educators, even like creatives from Creative Lab. And really what I'll talk about is the power of representation of characters in children's books and how we've been experimenting with certain technical models and AI models to actually diversify the narrative and characters in children's literature. Next slide, please. So yeah, engineers are boys. That's something my daughter, who was 4 at the time, had said to me. She is 7 now. And what was really alarming was the fact that, you know, she was able to distinguish between what is a girl and what is a boy by people's physical appearance. The backstory here is I was on a work call. So much like what we're doing today, I was working from home. She was not well. She was sitting with me and she asked me the names of all the people that I was talking to. So I would go, oh yeah, that's Mark. He's an engineer. That's Michael. He's an engineer. That's Kurt. He's my engineering manager. So there were 10 people on the call. And then at the end of it, she goes to me, oh, Mama, all engineers are boys. So I told her, you know, I'm one. I am a software engineer by background. But she chose not to believe that because for her, the context of people who were, you know, brainstorming on a call was more relevant than the context of a person sitting next to her. So she chose to believe the other context. Krishna, next slide, please. So when I started researching or reading more about, you know, why do these biases form? When do they form? What can we do about it? There were certain things that jumped at me. So we know that girls, there's enough study published out there about girls starting to doubt their STEM intelligence as early as age 6. But the thing that was new to me is that less than 5% of kids' books actually feature people of color in lead roles. And a lot of the time when these characters are present in books, they actually do not have a voice. They are very passive in the background. And there are very few efforts that exist to actually inspire kids under the age of 7, which is the pre-K to grade 3 bracket. And by that time, a lot of, you know, social bias and a lot of social damage has already been done. Next slide, please. So here are some stats taken from diversebookfinder.org, which is a nonprofit that's dedicated towards diversifying children's literature. And it shows you really the lack of representation in children's books with respect to BIPOC characters. And, you know, a lot of these stats that you see here are actually, I mean, real stats are actually much more dismal than this because these stats just measure the presence of characters. They don't even measure the portrayal of characters or their voice in books. Next slide, please. So, you know, when I was talking to people in my 20% team and my, you know, other people at Google, what is it we can do to tackle this problem? And we were beginning to form our 20% project. I was reminded of Dana Scully. And so I grew up watching Dana Scully in India. You know, I was that one odd girl growing up in India in the 80s who was allowed to watch this sci-fi show and allowed to have access to this character. And she was my role model. And much later, I discovered there's this study called the Scully effect, which says that, and it was a study done by GDI, that's the Gina Davis Institute, and Universal, I believe, whereby, you know, they studied and they published that more than 70% of girls and young females who grew up watching Scully as their role model ended up having jobs and careers in STEM-related fields. And, you know, I am a live example or a live byproduct of the Scully effect. And there was very little resemblance. Like, she had blonde hair, I had black. She was white, I was brown. And yet the fact that, you know, there was a woman doing these amazing things was, I guess, amazing enough for me to feel that I could do those amazing things too. So I was reminded of the Scully effect. And yes, next slide, Krishna. And, you know, when we read more, we had enough evidence, anecdotal evidence and research-based evidence to that suggested that, you know, when children or when people see themselves as the hero of the story, they are inspired to do a lot more. You know, inspiration is a prerequisite to learning. And this is where technology and media play a very important role. And when effectively designed, it can catalyze learning by providing personalized socializing opportunities, which has never been done before. So it's a huge way to engage children. Next slide, please. So we were having conversations with our friends in DNI, and, you know, they were talking to us about how they visualize a child's journey as cradle to career contextualization. So things that people do while they're very young, what are the impacts it has on them in terms of their career choices? And while talking to them, we realized that, you know, using characters and books, which is what children access very early in their childhood, we could probably replicate the Scully effect for young kids via reimagined books and, you know, more immersive technical modalities, and create a little microenvironment for them where childhood is magical, technology is whimsical, and representation is monumental. So that was our goal, to create this little microcosm or environment for children. Next slide. So in order to do that, we first published STEM books. We wanted children to have access to a world where they could sort of read about non-traditional narratives about engineering problem solving, about startups, about AI. And we wanted to present characters in this book that are based on real life AI scientists or real life engineers from very diverse backgrounds, so that children could see themselves reflected and represented in these books. So the first book actually published a few years ago. The second book in the middle came out just a couple of weeks ago, and then the third book is supposed to come out sometime next year. Next slide, please. And, you know, the intent, like I said, was to introduce children to characters that they are hard-pressed to see elsewhere. And these characters who look like them, but are also based on real life superheroes, so to say. So what you see here are some of the characters. The one on top are actually real life engineers who are from Google. The second at the bottom are real life tech founders from very diverse backgrounds from all over the world. And, you know, there are a lot more such characters. Next slide, please. And then we wanted to sort of also, you know, present characters that challenge stereotypes and bust stereotypes. So, you know, what would you think of when you think of a tech disruptor or an angel investor? Would the first impression that come to your mind be any of these characters that you see over here? Likely not. So we introduced angel investors and tech disruptors who look like what you see here in the books. We have this team of super solvers. This is a diverse squad of solvers in the book, and, you know, they are from a spectrum of ability, appearance, racial backgrounds, and whatnot. What you see at the bottom is an attempt to introduce an indigenous character to the children. And, you know, the reason I put that in there is because we actually had to go through a number of iterations to design a very authentic character that was not a westernized version of an indigenous person. So what you'll see at your far left is the first version where the character was wearing a feather. And when we consulted with some indigenous elders, they made us realize how that is actually not very appropriate and disrespectful. And we went on to do many iterations to come up with a more authentic identity for the indigenous character that kids could relate with. Next slide, please. So yeah, this was just the book, and the books have been published in a number of languages around the world. And we started seeing a lot more, a lot of fan mail from children, and especially girls and people of color, who sent us so many stories of the amazing things they wanted to do by reading the book. And what we really discovered, the key insight, was that children love relatable characters. When they can see themselves in the characters, they love the story even more, and they're inspired to do even more things. So there's one little story that someone sent. My adventure is to make a spaceship to go into someone's brain to cure diseases. Yeah, so those are the kind of wild things that kids can think of. Next slide, please. So we wanted to take that discovery to the next level using technology. How can we experiment with technology towards creating more immersive environments for storytelling? And how could we potentially diversify characters and narrative at scale to address or to reach to more children? So next slide. So then we partnered with a lot of other teams at Google to actually take the story from 2D to various other modalities. The first one that you see is a VR expedition that's based on the book. So children could now, whatever they had read in a 2D book, could actually see in a 3D manner. And it's funny that that's the first time you would see children realize something like that a data center is a really big thing, whereas a microchip is actually a very small thing, because in a book they look more or less the same. So it was the first time that children were able to actually make that comparison. The second one is an assistant read along that's based on the book. So, as children are reading stories, there are certain keywords that trigger sound effects on the assistant. And, that really allows them to, and this is something we discovered later, it allows them to make these associations which they would not otherwise make easily. So a lot of children would think that coding is a thing you do with your eyes, because your eyes are always moving when you're coding. When they were reading the book with the assistant, they realized, oh, coding is something that produces typing sounds, so it must have to do something with the keyboard. So those are the kind of associations kids were able to make. And then there was themed curriculum that was based on the book, which actually inspired kids to, deconstruct a computer. Because the computer, like there's a robot in the book, and that robot is essentially a computer, and they were more keen to deconstruct something that is a robot and discover its parts. Next slide, please. Yeah, so the other interesting experiment that we did or are still doing is we used certain AI models to actually morph characters, to morph the popular characters to look like underrepresented kids who are reading the books. So the first one that you see is actually of a little girl who has alopecia, and that girl probably has never seen herself reflected in a real book. So what we were attempting to do was, what if we could morph the main character, Ara, in this case, to look like that girl, so she could see herself as the hero of the story. There are a few other experiments that we did. So what if a girl, and all of these are sort of non-traditional looking faces, and people who are girls who do not see themselves in books. So what if a girl had green hair? What if the girl was wearing a hijab? What if a girl had really coily hair? So we actually created a prototype, and this was done during a hack week. And as the next steps, what we are trying to do is, next slide, please, Krishna. We're actually trying to take it towards, productizing, possibly. So working with a few areas at Google with photos, and of course with the research group, as well as playbooks and Stadia, to see if we could use this to diversify characters at scale. Next slide, please. So yeah, some future directions also that we are exploring. Next slide. So so this is interesting, and that is measuring representation in kids' books and media. So I actually know librarians who try to do this in a very manual way. They look at books, they actually audit the books themselves, and then they try to come up with or record stats on what is the level of representation in books. But of late, we've been made aware of certain researchers at University of Chicago and University of Virginia who are trying to do this in more automated ways to measure representation in books using NLP models, as well as using image models. So, that's an avenue where we're beginning to think more about, and we're trying to partner with nonprofits such as Diverse Books Finder, as well as researchers to be able to measure this at scale. Next slide, please. And yeah, this is still very experimental and very abstract, but I personally am very interested to, come up with ways in which, when children think of stories, they have a very wild imagination. But when I think machines think of stories, or when we ask machines to create stories, they're probably more biased stories. So I'm trying to see if a child's imagination can be used to train a machine's imagination. And if, we can, use things like, come up with things like auto-arting. We're using AI to enable children and writers to generate illustrations on the fly, right? And these illustrations would then in turn be things that are very, very atypical. Children would probably come up with ideas such as, there's a princess who has unruly hair and she loves to code. Whereas if you look at traditional ML models, they probably will, and you ask them to generate an image of a scientist or a doctor, they probably would not generate the photo of a princess, right? So I feel like there's an opportunity to actually use children's imagination to train our machine learning models. So that's an area where we are just at a very high level beginning to brainstorm and explore. Next slide. And that's about it. Thank you for your time. Hopefully this was insightful and helpful, if not wild. Thank you.
Thanks, Komal. This was great. All right. So let me, if I may request all the speakers of this series to just turn on your cameras. So we'll take any questions or points of discussion. As before, if you can use the raise your hand feature or post your question on the chat. Question by Sabi. Sabi, do you want to ask the question?
Okay, so there's a question. I can read that out. Or Krishna, do you want to read it out?
Yeah, I can read it out. For Komal, what do you think is more inspiring or important for encouraging female participation in STEM? Reading books or watching movies with strong female portrayals in STEM, or informing or educating them about real-world examples of famous female STEM persons? Oh, sorry, I didn't read the mic. Mic is dead. Okay.
Yeah, so I think it's all of it. I think it is a multifaceted problem, very multi-layered. And I think it's not just about making children and girls more aware of the opportunities. It's also, I feel, about sensitizing the parents and the elders to provide a bias-free environment for them to excel in, expose girls to coding just as much as you would expose them to music, and then let them make a choice. And by the way, I feel like these stereotypes apply not just to girls, but they apply even to boys, right? Like there are certain things boys are sort of conditioned to do more, and we also don't let them make free choices. So yes, as much as it's a matter of girls in STEM, I think it's a universal matter of let children be and explore on their own. Morgan says, does your daughter not believe that engineers are also girls? And Morgan, so I'll give you an example. we had the good fortune of going to China for the book launch of the Chinese version, simplified Chinese version. And there was a journalist there who asked my daughter, so what do you want to be when you grow up? So she said, I want to be an engineer and an author. So yeah, I think she believes that she can be an author and an engineer at the very least. And Morgan,
Great.
thanks for joining. You have a small baby, so it means a lot you joined.
Cree.
Yeah, thanks to all of the lightning speakers. They're super interesting talks. I kind of wanted to, ask you, Amy, maybe a bit more about the connection to the sort of media theme here. In your talk, it felt a lot like, well, first of all, it was incredibly insightful. I was getting goosebumps through parts of it, but like the examples of how using technology to mediate some of these experiences of climate change maybe are less effective than the embodied experience. And so I'm kind of wondering, what is the role for media in this whole process of educating people, or just dealing with this overwhelming issue that we're all facing.
Thank you, and thank you for your question. I think it inevitably has to be a part of it. It's the question, I think, is how to make it an effective part of it. And so taking parts of the examples where they're all obviously working towards the same goal, but some of them are more effective than others. And so trying to, and that's kind of why I had the example of, the kind of wearable technology at the end, because that seems to, kind of bring all those elements together in terms of, kind of like using your, potentially using your smartphone as a tool for reading the technology that you're gathering through the sensors that you're wearing, and how that interacts with your role in the world, and what that means for what's happening above you. But yeah, I think a lot of people see this kind of like nature culture divide, and that's just kind of not really realistic anymore. Even if you want, and as I was kind of vaguely referred to with the research that I did for my master's, in needing to kind of like escape into nature and those kind of things, we need increasing amounts of technology to do that in a safe way, and to enable access for more people. So I think that kind of trying to not fight that divide as much, but embrace it, is kind of where I see there being potential going forwards. Yeah, thank you.
Thanks, Amy. Sarah, I'll come back to you. I have a question from Makran here. I'm eager to understand whether you see, for Komal, I'm eager to understand whether you see physical books being individualized through such means at some point, like print your own book style, or how does the wonder of actually flipping through a physical book compare against using a digital version?
Yeah, Makran. So I personally love flipping through books. For me, nothing replaces that magic. But at the same time, I understand that the younger generation, they are growing up with a very different mindset. I mean, I cannot speak for the masses, but I know that when I see my children, they do love reading books, but they want something beyond that. Like, they want the book to continue in other dimensions also, because they're very comfortable with other dimensions, such as media and even like mixed media. So I feel that, as important as books are, for them to stay even more relevant, I don't think there's harm to take them in sort of a mixed media medium. That's my personal take.
Sarah?
Yeah, thank you. I had a question for Morgan. I was wondering if you could talk a bit more about the sort of component of the values that are being expressed, and in particular the silenced values piece, because I think that that's really important and often kind of intuitive. And how do you talk about that when you're analyzing these data practices?
Yeah, thanks. So a question of just generally, how do we talk about the values that are silenced, or
just if you could talk about both like what kinds of things you saw coming up in terms of which values get silenced, and then in your own practice of analyzing these data sets, yeah, like which values get silenced, and then how do you look at the sort of meta-analysis that you did to figure out how do you go from, okay, these are the data sets we had, to how do I actually read into this to figure out which values, like how do I move from, okay, I can tell from looking at this that this data is effed up, but like how do I actually do this in an empirical way so that I have the science behind me so that I can explain this.
Yeah, I feel like it's a really like it was an iterative process. So kind of what we started with in terms of, it was really identifying the values that existed in the data sets. And so that really started with a lot more of a structured coding approach. So it was, what are the things that we are consistently seeing coming up when we're reading documentation about these data sets? And things like that tended to be statements about, oh, this is how we controlled for bias, for example. So that it became obvious that objectivity of some sort or neutrality of some sort was really valuable. And as a result, the silence values were implicit, obviously. So they weren't saying, oh, subjectivity is bad, but they were, through valuing consistently objectivity, there was kind of this inherent critique of positionality as valuable. That was always viewed as sort of making the data less valuable to their audience rather than more valuable to their audience. So that's kind of how we did it. I can also look up and link to the codebook, because the codebook has like 100 something values in it. Not all of the, like, it's very hard to kind of summarize those things and how they came together, because it was also a means of like, well, we saw this many papers said this, but also qualitatively, what did they say? And so it was kind of this really messy qualitative / structured approach to this. I don't know if that's super helpful. It's really hard. I'm doing something similar now, and it is very hard. I'm like teaching a master's student who's interested in grad school or in a PhD how to do this. And it's like really hard to do because it just feels very messy and intuitive, even though it's empirical, and it's, yeah, it's, I hope that's helpful.
Thanks, Morgan. I have a question from Makaran here for Morgan. Want to understand your thoughts on this emphasis becoming more accessible to academia as well, where collecting data from scratch is not always easy. And Flickr and YouTube provide easy ways to start with something quickly. The emphasis being data work over model work.
Yeah, I mean, I think it's, from my perspective, it's, I guess there's a level of like Flickr and YouTube being easy and also cheaper for academic institutions, whereas, you know, larger, perhaps corporate institutions have more money to put towards maybe consensually collecting data, which is understandable. And this is something that I've also done in previous studies. I used Instagram to collect data, but we did include a large statement of what is the reason that we chose to do this, despite the fact that it's ethically questionable to just collect that data. And I think it would be contextual based on also how is the data being disseminated, if it's being disseminated, how is it being, is it getting embedded into a bunch of models that potentially the data subjects and copyright owners don't know about? Those are all kinds of ethical questions that I think academics should be contending with more, and currently they're not in machine learning practices. In terms of making that, I think the accessibility issue is more about making that thinking accessible to Computer vision, particularly, I can't speak as much for NLP. I've generally heard that they are contending maybe more with these kinds of issues than the computer vision community is. So I think it's more about, okay, how can we encourage this thinking in the disciplinary practice of computer vision? Because I don't think it's always necessarily inappropriate, although ethically questionable, to use public data. It's more about, okay, why am I using this data? What is the benefit I'm getting in using this data? Is it more beneficial to do this versus not do this? Those kinds of questions. And in terms of teaching, I think that's really difficult. I have another fact paper with Deb Raji about this. It's just like, what do we teach when we're teaching ethics? And a lot of that is already in the hands of computer scientists rather than people who are situationally trained to understand ethics in certain contexts, perhaps gender studies or global politics, like those types of things. So the actual solution to teaching that to the future engineers or the future professor in computer vision, I think that's the more difficult thing, actually. I don't have a great answer for it.
Thanks, Morgan. Digbale?
Yeah. Hi, Komal. Thanks for the wonderful talk. So I was looking at the examples that you showed for the character Ara. So I was thinking, can we have like an interface for the young reader itself, and they can personalize the story, and we can use that as guidance for the narrative rather than just get their feedback, like how they want to see themselves, and use that for curating the stories.
Yeah, that's a great question. So, one of the things that we did to plot book number 3 is actually we invited ideas from kids. And of course, this was a bit, manual. Like they had to submit forms and teachers had to submit on their behalf. And we got some good story ideas on, what they wanted for Ara's next adventure to be. But yeah, it's certainly a good direction. I can't say I've thought about it deliberately, but yeah, there could be ways that children can actually personalize stories or even come up with the next version of the book. Yeah, so it's something to think about.
Okay. Thank you. Yeah,
thank you.
Thanks, Komal. Oh, my 3-year-old niece's birthday is next week, so I'm totally getting her the VR headset.
Awesome.
A quick question, a follow-up for Morgan. Morgan, you talked about generalizability and contextual. But I was thinking about what happens if we prioritize contextual over generalizability. Would that end up providing more accessibility to models as well as data to certain communities, and certain communities end up getting underserved?
Yeah, I mean, I think that's possible. I mean, I think in practice, a lot of companies at least are using highly contextual data for highly contextual problems. So, I mean, we were looking at academic data, so I think this was coming up less, where the academic goal is how can we create the future of AI to be this generalizable thing that can classify anything and be useful in a number of contexts. Whereas if you look at, I don't know, there's a lot of just like, how do you classify documents in a certain language used in like the commercial world? I mean, I think that probably is true, but also the generalizable models also have this issue in terms of accuracy or underserved groups. So that is constantly what we see even in large data sets like ImageNet or Tiny Images before it was removed had a lot of really offensive terms to specific subgroups. So I don't think that the generalizability versus contextuality necessarily privileges one over the other in terms of what will happen in terms of marginalization, because both probably have that issue. But I definitely think it would have to, I mean, just like we should now with these giant data sets, we should have to pay attention to those things. And again, I think training people to pay attention to specific groups is very, very hard, because obviously it's easiest to think about what is your experience? What group do you belong to? Therefore, we should include those groups in our data set, while other groups or other contexts will always kind of be more difficult to understand. And so I think that again is just it's a training thing, but also who is participating in these spaces type of thing. So again, not easy solutions, more like more problems to think about.
Great. Thanks, Morgan. Sri?
Had also a question for Morgan. Morgan, one of the things that you said in this broad aspect of contextualizing data, especially in the context of machine intelligence, where you said like one of the recommendations was characterizing the people that provided the perception of the people that provided the sort of the information, like demographics. So would you elaborate a little bit on that? Right, it's a very important thing. We all kind of know how to bring sort of models of the annotators into the picture, but how to do that has operationalized that has been sort of very tricky. So how would one sort of take right associations that are reflected there, right? Like again, right, they say some aspects of demographics you have the information, but how would one go about doing that in a way that truly is informative or serves the purpose? So love to hear your insights there.
Yeah, I mean, I think it's difficult because the way that we generally collect demographics is structured in a way that is very specific and reaffirms very specific views on things like identity, right? Like it's like, oh, we use the US Census for race, we use the gender binary for men and women. It's just reaffirming that those are the categories. And I don't necessarily think that is the correct way to go about it. Potentially that is the way someone would go about it if they were like, oh yeah, I should include my author demographics, I should include my annotator demographics, which surprisingly we really didn't see very often. It was mostly subject demographics that people included. So I think what to me would be really useful is just like, okay, as an author or as an annotator, what is the type of data I'm providing in this data set, and what are the identities relevant to that information that I'm providing? So I'm trying to think of an example. Like there's quite a few data sets that are including just somebody else annotated ethnic categories. So I want to know, well, what is the expertise that you have as an annotator to be doing that work? So it would matter what ethnicity you are when you are assessing the ethnicity of other people. And that that would apply to whatever group. So just thinking through more the relevancy of, what are your identity categories that make your perception of the data change, because all identity categories do that. And this is also hard because I'm very good at coming up with tensions instead of answers. This is hard because there's been a lot of talk about enforcing people to, have positionality statements is also problematic, particularly for marginalized groups. Like you shouldn't have to constantly be asked to do that. So that's another kind of tension that's like, well, we can't just keep making marginalized groups make positionality statements in their research. Generally, that seems to be who is doing that work rather than, the majority group. So that's kind of another tension that's like, well, is it even appropriate to do that? It should definitely be. Yeah, I don't know. Again, I'm just bringing up a lot of things to think about more than things that are answers or solutions or checkboxes.
Thanks much for that. That's precisely the idea of this workshop, right? Thank you.
Great. Thanks, Morgan. Any other last questions or comments or discussion points? All right. Going once. Okay. If no other questions, let's great discussion, everyone. Let's thank our speakers again. And don't go away. We'll take a quick 5-minute break, and then we'll be back for the next set of lightning talks. We will resume in exactly 6 minutes at noon Pacific time. All right, let's give it a minute as everyone is coming back slowly. Let's give it a few seconds. Great, let's start off the second series of lightning talks. We have 3 more speakers in this lightning talk series, Ronak Kosti, Aida Dawani, and Digbal Bose. As before, each lightning talk is 10 minutes long, and hold your questions and discussion points until the end of all 3 speakers. With that, also a reminder for the speakers, if I may, please introduce yourselves before the talk. With that, I'll hand it off to Ronak.
Thanks a lot, Krishna. I'm happy to be here. Myself, Ronak Kosti. I'm a postdoc researcher at Pattern Recognition Lab at Friedrich Alexander Universität Langen-Nuremberg in Germany. And today I'm going to talk about a data set that we created together with my co-authors. One of them is Agatha Lapidrisa, who was a speaker in your previous version of the workshop. And therefore, I'm happy that she could recommend me. So today, in this talk, I'm going to talk about emotions in context dataset, which is very well situated for this workshop. And you will see, because you've seen Morgan's talk, that a lot of the ideas that he discussed, it's a very good chance to take an insight into how we have built the dataset and compare. So I'm happy to follow his talk. Follow the previous talk. Okay, next talk, please. Next slide, please. So the motivation is we want to perceive people's emotion in our everyday lives, and how to do that through images. That's our main motivation. Next slide, please. In this, context is very important, as we already have seen through multiple talks, where we are situated, where we are located, with whom we are interacting, and things like that. So when we look at only the face of the person, we on the left-hand side here, we see that maybe the person is happy. But if you get a more information like the full body of the person, then we see that the person is looking somewhere, and we see that the person is anticipating, maybe excited about something, towards something. Next slide, please. And when we see the entire context here, we see that the person has actually, won some competition and is very happy and more confident about it. And therefore, the more the context we get, the better understanding we get of what people might be feeling in their situations. Next slide, please. So the main idea of building this data set, we have a situation given, we have a person in the bounding box for whom we want to predict the emotions. And yeah, that's the main idea here. Next slide, please. So in this, I will talk about how we generated the data set. Next slide, please. Emotic is short for emotions in context. Next slide, please. The first stage is obviously collecting images. So we collect images from multiple sources like AD, 20K dataset, COCO, Common Objects in Context, and Google Image Search. And in each of those images, we already had the person annotated in a red bounding box as shown above. Next slide, please. And so once we have the image and the people inside them, what do we want to know about their emotions? So we came up with two different representations, which kind of are complementary to one another. One is a discrete way of representing emotions, 26 discrete categories. And one is a 3 continuous dimensions, which represent intensities of 3 different dimensions. Next slide, please. For 26 discrete categories, we started off with the 6 basic emotions proposed by Paul Ekman, and we added more affect words related to these emotions, and then we increased our vocabulary through word search and word relationships search. Next slide, please. And therefore, we added 20 more affective categories to the 6 basic emotions proposed by Paul Ekman. Next slide, please. And this is an example of all these 26 categories and their associated affective related words, affect-related words and meanings. And therefore, for example, when you see affection, it can mean fond feelings of love or tenderness. Next slide, please. Here is an example of a person annotated in the center of the image, where the annotator has labeled this person's feelings as anticipation, excitement, and engagement. And you can see different affect words associated with each of these emotion categories. Next slide, please. And then we also have 3 continuous dimensions. First is valence, second arousal, and dominance, where valence essentially means how pleasant or unpleasant the person is feeling. Arousal is about the activeness of the person, how calm or active the person is. Dominance is essentially about how much you feel the person is in control of the situation or not. Next slide, please. And so here we reflect the same ideas. Valence, here we see that the person is a bit more on the positive valence side. In case of dominance, we see that the person actually looks very much in control of the maneuver of the slide. So therefore, a very high value of dominance. Next slide, please. And in order to get the annotations or the labels, we went to the popular crowdsourcing platform, Amazon Mechanical Turk, and we created a qualification test to qualify different workers based on 2 ideas. First is the emotion quotient. We asked them 28 different questions. Some of them mentioned here. We take it from a very popular study. These are very simple questions to answer, and based on their values, we compute their emotion quotient. Next slide, please. In those questions, we also add 2 control questions where we ask like factual answers. So we know whether the annotator has responded truthfully or was it a random guess for all the other previous questions. Next slide, please. And then we ask them 2 different questions. One is a categorical task and another is a continuous dimension task. In categorical task, we ask them to annotate or pick as many emotion categories applicable for the person in the context. Next slide, please. And for continuous task, we ask them to choose the intensivity values for valence, arousal, and dominance. In addition to this, we also ask them the perceived gender and age of the person in the context. Next slide, please. Not only that, for each of these tasks, we have some instructions available for the annotator, which the annotator can refer at any time if he is in confusion, and also a very simple example of what could be a correct label and what is not a correct label. And the annotator can refer to whenever he is in confusion. Next slide, please. And next slide, please. Yeah. And now we go into a bit of statistics of what we have in our data. We have around 35,000 people annotated with a split of trained, validation, and test as 70, 10, 20% respectively. And validation set specifically has 5 different annotators for each person. So we have 5 different annotators annotating the same person. Same for similarly for test, we have 3 different people. Here in the graphic, you can see on the y-axis it's a log scale, and therefore you can see that engagement has more than 50% representation in all of the images. Next slide, please. Similarly, for valence, dominance, and arousal, the distribution across different values, we have we show this in this graphic. We can see that it's fairly evenly distributed. Extremes are obviously, very difficult to capture such moments, and therefore you see less representations there. Next slide, please. And then we also see some co-occurrence of different emotion categories. Advance the slide, please. Here, for example, for each row, you can see which column emotion category is co-occurring with that emotion. For example, for all the images annotated with affection, there is a probability of 67% of images having also happiness annotation. Advance the slide, please. And you can see that for happiness and anger, this is a very low value because it's very rare that the person would be annotated with happiness as well as anger. There is still a small percentage chance here because it's possible that because it's a subjective annotation, one annotator might have seen an extreme end of the emotion. Next slide, please. Similarly for the distribution of, no, next slide, please. Similarly for anger and annoyance. And here we see the distribution of valence values across different emotion categories. On the x-axis, you see on the left, the lower valence values, and on the right, the higher valence values. Clearly, when there is a positive valence values, you can see categories like happiness, affection represented there, whereas with lower valence values, you see emotion categories like suffering, pain, sadness, like negative categories being represented. Next slide, please. And here we talk about the annotator's agreement now. So we use Fleiss' kappa measure, which measures the agreement level between more than two annotators in an image. Here is an example where we see affection and pleasure being chosen by all the annotators, engagement and happiness being chosen by only 3, and excitement only by 1 annotator. Here the kappa value is very high, it's 0.73. Next slide, please. Note that this is a lower kappa value, 0.24, where you see very low agreement between the annotators. However, when you see the individual categories selected, all of them kind of make sense from one perspective. So even though lower kappa value, we still have good, meaningful annotations. Next slide, please. And this is the distribution where we see that more than 1,500 images in the validation set are having a higher kappa value than 0.3. Next slide, please. Next slide. Okay, so next is in the images that we have in the emotic data set, we want to see what are the different categories and what are the different scene attributes related to those categories. So we want to analyze the context, the situation that is present in the images of emotic. So for this, we essentially want some scene category labels or some scene attributes labels. Next slide, please. And for this, we use a pre-trained deep learning model, which is taken from the Places dataset. Places dataset is essentially a 10 million labeled images dataset with 365 places categories, as well as additional scene attributes. And we use this model to get the scene attributes and scene categories predicted for each image in emotic dataset. Next slide, please. Here we see the distribution of different emotion categories for the scene category named bedroom. And as you can see here, categories like pleasure, happiness, and engagement and excitement are also very high probable in this kind of scene category. Next slide, please. We see similar distribution across different scene categories like office, hospital rooms. Specifically, let's see baseball field. Here you see categories like anticipation, excitement. These kind of categories more prevalent. Next slide, please. Same for emotion dimensions. When we see the arousal emotion dimension, where the higher values of arousal are occurring in scene categories like ocean, baseball stadium, football stadium, and places like that. Whereas for lower values of arousal, where there is a lower activity in general, it's like hotel rooms, some different kind of rooms, conference room, dining room, hospital room, things like that. Next slide, please. This is another example for scene attributes for the distribution of emotion categories across the emotic dataset. Here we see, again, for competing attribute, we see confidence, anticipation, excitement, having more probability across the dataset. Next slide, please. And same for other kind of scene attributes we see for emotion categories. Next slide, please. And the same thing for emotion dimensions. Here we see that for lower valence values, we see scene attributes like enclosed area, competing, dry driving, working, things like that. And for higher valence values, we see snow, sailing, boating. So essentially more attributes which are associated with high activity or more positive experiences. Next slide, please. And that's it. So that was the talk about how we generated our emotions in context data set. And for more details about implementation of convolutional neural networks, how we model these emotions to predict the perceived emotions, please refer to this transactions paper. We also have a workshops paper exactly about this data set. So if you're interested only in the data set paper, you can refer to the data set paper. Next slide, please. And data and code are available on the website as well as on the GitHub repo. And that's it from my side. Thank you very much.
Great. Thanks, Ronak, for the great talk. Our next speaker is Ida Dawani. Ida, on to you.
Thank you. Hi, everyone, and thank you all for being here for this talk. I'm Ida Dawani, and I will be presenting two recently published papers on dealing with annotation disagreement in subjective tasks. This work is the result of our ongoing collaboration with my amazing co-authors, Binod and Mark. Next slide, please. Here we look at the common practice of training supervised models based on the ground truth labels, which are obtained from the annotations. In most scenarios, especially if the data is collected through crowdsourcing annotation platforms such as Amazon Mechanical Turk, we obtain several annotations or labels for each instance. Next slide, please. And most often we aggregate annotations using majority word or just present the average or the distribution across the labels. Rarely we adjudicate and ask an expert annotator to resolve this disagreement. In all these scenarios, we are chasing a single ground truth because we need that to train the model. Next slide, please. However, in case of subjective tasks such as toxicity and emotion detection, there often exists no right answer, and individuals' perceptions of the toxicity or emotion might vary based on their individual differences. Next slide. Here we looked into a number of annotated data sets for subjective tasks and asked two main questions. Does aggregated data uniformly capture all annotators' perspectives? And does aggregated data reflect certain demographic groups' perspectives more than the others? Next slide, please. So for the first question, we analyzed 3 different data sets annotated for 8 different subjective concepts. 6 of these concepts are emotions, 1 is the sentiment, and the other is the hate speech. In these data sets, we explored the agreement between each annotator and the majority label. And for some tasks, next slide, please. For some tasks that are marked as green, most annotators had pretty high agreement with the majority label. Next, please. However, for some other tasks, such as annotating disgust and sentiment, this is not the case. And a substantial percentage of annotators' perspectives were not at all reflected in the majority label. It could be the case that these annotators are having like noisy annotations, but we argue that there might be some systematic ways for annotators to disagree on these subjective tasks, and their disagreement can be derived from their socio-demographic backgrounds or lived experiences. Next slide. We then analyzed whether the aggregated data reflects the perspectives of certain demographic groups more than the others. For this analysis, we could only look at one of these data sets, which was annotated for sentiment, and the data curation also included the socio-demographic information of the annotators. And it turns out that not all social groups' perspectives were equally represented in the majority label. While there was no significant difference along the binary gender axis, the majority labels had significantly lower agreement with annotators who identified as Black. This sort of disparity is different from what is entirely in the data itself. This is a disparity that is created based on our choice of aggregating the annotations based on majority votes. Next slide, please. So what we found was that the aggregated majority vote does not uniformly reflect the perspectives of all annotators. And these agreement scores may vary significantly across different socio-demographic groups that annotators identify with. Next, please. So therefore, rather than aggregating annotations prior to modeling, here we propose a multi-annotator modeling approach to predict individual annotators' labels for each input while keeping a shared representation of the task and leave open the choice of whether or how to aggregate. Next slide, please. We investigate multi-annotator modeling in a classification task where each instance is labeled by multiple annotators, and the goal is to predict the final label. Here we refer to this final label as the majority vote, but there are very different methods for aggregating annotations into labels that we haven't discussed yet. So in the baseline setting, the annotation aggregation is performed prior to modeling, and the model is trained directly on the predicted on predicting this majority label. On the other hand, we investigate 3 different methods for multi-annotator modeling. Next, please. So first is an ensemble, which includes single task classifiers, each trained to predict one of the annotator's labels. Next, please. This second one is a multi-label model, which learns to predict a set of annotations for each input in a multi-label framework. And the final one, next, please, is a multitask model, which learns multiple annotators' perspectives as separate classification tasks. All of these tasks share the same encoder layers to generate the same representation for the input instance. Next, please. So the multi-annotator model can help us calculate the uncertainty of the prediction as the variance of the predictions from different annotators. We investigate the correlation of this uncertainty with the annotation disagreement and compare it to 2 other methods for calculating uncertainty. Next, please. Namely, the softmax probability of the prediction, and next, the Monte Carlo dropout approach, which calculates the probability distribution of predictions by iteratively applying random dropouts to the model. Next, please. We compare the uncertainty predicted by the multi-annotator models on a data set of hate speech with the uncertainty estimated by other approaches. And the results shows that the uncertainty predicted by our models is more significantly correlated with the annotation disagreements. Next, please. We also found that uncertainty calculated by the multi-annotator model varies across different types of erroneous predictions of hate speech. So for example, next, please. For example, the average, on average, incorrect predictions of the hate speech and the multi-annotator model have higher uncertainty than the correct predictions. And when we look into specific kinds of error, next, please. We found out that the model is almost always certain about true negatives and uncertain about false positives. In other words, high uncertainty in the multi-annotator predictions can likely indicate some kind of false negative or false positive predictions of the model. Next, please. So does this hurt the predictive performance of the model or the time complexity of creating this prediction? Next, please. So here we compare the accuracy of the multi-annotator models to the baseline on 2 different subjective tasks, one hate speech detection and the other for emotion detection. So for the first task on the hate speech detection, and during a 5-fold cross validation, over the data set, we show that the multitask model performs better than, significantly better than the baseline and other multi-annotator models. And impressively, next please. Impressively, the multitask and multi-label models do not take significantly more time to train, and the increase in the computation time is only marginal compared to the baseline model. Next, please. Yeah, and for the emotion detection task, which was performed on 6 different labels, next, please. Surprise, sadness, joy, fear, disgust, and anger, we showed that the multitask model is doing better than this baseline on most of these tasks. Next, please. So here we investigated a multi-annotator approach, but there are some limitations to the model that we discussed here. So for example, as you saw, the ability to predicting the majority label varies across tasks. And for example, in the emotion data set, we couldn't predict all these emotions as good as the baseline model. Also, this modeling is not feasible when there's a huge number of annotators, because it's not possible to train such a big model with so many layers. We discussed some of the possible approaches for dealing with issues, such as grouping annotators based on their sociodemographic groups, or maybe grouping them based on some psychological aspects that can relate to the annotation task itself. Another limitation is that we need a large number of annotations from each annotator, for example, more than 1,000 labels, to model each of these tasks separately. And this cannot be done when, for example, in crowdsourcing frameworks where annotators only annotate a small set of these items. Next, thank you so much for listening. And yeah, this was a collaboration between USC and Google Research. Thanks.
Thanks, Ida. It's really interesting findings.
Thank you.
Our next speaker is Digbalai Bose. Oops, sorry about that. Our next speaker is Digbalai Bose. Digbalai, on to you.
Thanks, Krishna. So yeah, I'm Digbalai. I'm a 4th-year PhD student at SAIL Lab under Professor Sri Narayanan. So I'll be talking about understanding context in movies, taxonomies, benchmarks, and challenges. It's an ongoing collaboration between SAIL and Google Research. So next slide. So just to give an idea of what is context, because this is like the whole theme of the workshop, and it kind of builds on what Ronak showed and previously Dr. Tapaswi mentioned. So context is essentially actions and responses are influenced by the situation in which we do it. And that situation is essentially what we can call the context. So if I can point to a couple of pictures here, on the second picture here, how you recognize objects, you can see these are the same letters, but based on where they're placed. In the first part, it's showing it's A, and the right part, it's H. In the last picture, you can see if we just take the face into account, it shows anger. But when we take the entire context, this shows triumph because the person has won in a match. Now, context also drives responses in social situations and also how we perceive popular opinion about places. Next slide. Now, to give an idea of how visual scenes can be important for context, usually when we think about a scene context, it's highly centered around objects and how they are spatially co-located with other objects in that environmental location. Now, when we think of a scene, you can see for airport and stadium, each can be considered as a prototype image. And with that, we have multiple views or multiple variations, which can be considered as different exemplars. And each scene can be thought of as contextually coherent if they have items or objects that occur together in similar configurations. For example, if we take airport, we have planes and landing docks and reservation counters. All these are contextually adding context to the specific scene. Next slide. Now, in terms of movies, I just want to build upon what I described for visual scenes. The context might cover a lot of different aspects. So here's a single snapshot from a movie, Sleepless in Seattle. So if you just look at this snapshot, it's showing like it's an event that is Christmas. And also the location is a dining room, which is an indoor setting. And you have an action that is going on eating. So this is difficult to, we can see from the picture, but when we look into the clip itself, we can see the actions in context. Now, if we take, next slide. So essentially, location and setting we can consider as the scene understanding problem here. And that would be like the next part of the talk. Now, what are the different aspects in scene understanding if we consider a movie? So it's usually not a static representation. You can see within this scene in road, multiple actions are taking place, like opening a car and talking. Also, consecutive segments, you can have scene context change, like there is a sharp change from a sky space shuttle to a control room. And also, if you just take a particular scene, there are a lot of other attributes, like whether it's happening inside or outside, and what's the time of the day. And also, for example, how the characters are portrayed. In the first picture, you can see in the conference room, it's like completely predominantly male dominated scenario. So character portrayal has another associated attribute along with the time of day and the interior or exterior part. Next slide. Now, before we talk about how we can think of developing a taxonomy for movies, I just want to point out the timeline of the different data sets that have been released and with scene annotations or location annotations. So it started with Hollywood to Scenes dataset in 2009. And currently we have, it progressed from Movie Graphs dataset, which was mentioned by Dr. Tapasvi. And then currently we have a lot of data sets in the domain of short clips. So these are essentially condensed movies, and VidC2 are essentially data sets which are extracted from Fandango movie clips, and they are concentrated on short clips with like places of actions and descriptions. Next slide. Now, what are the challenges associated with these data sets? So for example, in multiple cases, background information might not be present, and it becomes very difficult to understand where the location is. Also, if we just take consecutive shots in the same clip, it might happen in two completely different locations. But if you just take the description from the movie clips site, it's mentioning a single location, whereas it should be multiple locations per shots. Also, you have a lot of variety within a same location based on the style, whether it's animated or non-animated. Next slide. Now, the question comes, why do we need a new taxonomy for movies? So as we know, taxonomies are in general not complete, and movies do reflect real world and both fictional scenarios, like for example here, Office and Spaceship, two different movie clips. And existing scene taxonomies often do not consider movie-specific locations like control room or war room, and there are a lot of mentions of generic locations like sky, which might hamper understanding of the model in like downstream tasks. Next slide. So the question was, how can we use different sources to curate a taxonomy? So what we did was we took two sources. One is a domain information from screenplays. So essentially we took slug lines, which are like master scene headings, which provide information about the interior and exterior and the location of scene and the time of the scene. We semi-automatically extract like 156K slug lines from 1K movies. And from there, we extract mentions of 173 unique scene labels. Also, to go into the domain of video datasets with scene levels, we leverage this current work from ETH Zurich called Holistic Visual Understanding Dataset, where we take like take the 248 scene labels spread across 481K videos. So now we have these two sources. Our next goal is to find out a holistic taxonomy for the entire movies. So what we do in the first step is we just extract out the common label space between HU and slug lines. Next. Now, after extracting the common label space, we have two separate parts in both HU and slug line taxonomy without the common label space. So how can we merge that into a single space so that we can have a unified representation? So we extract the label representations using sentence transformers, and then we take like top case similar labels for individual label using cosine similarities. Then we have like a label pruning setup by a human expert. For example, in the label pruning setup, we consider wiki definitions to merge confusing labels like bazaar and market. For example, bazaar is a special form of market which sells local goods. So we merge these examples into a larger label, like for example, market here. Next slide. Yeah, so that is, so now the insights into, yeah. So we have some couple of insights into the movie taxonomy. So how much is the coverage from movie scripts? How much is the coverage from HView, and what's the common label space? So you can see like around 43% comes from the slug lines, that is from screenplays, and 16% is from HView. So there are a couple of like generic labels, sea, road, skyline. And there are common labels, around 68 labels between slug lines and HView. So beach, forest, and living room. Next slide. Now, once we have this set of labels, the question was, can we have a set of hierarchy? Should we manually enforce it, or should we try to extract it automatically? So we use again the label representations, the embeddings that we extract from sentence transformers, and use affinity propagation on that to find out the hierarchy or the groupings. So you can see there are like some logical groupings here. For example, river, pond, pool, pond, waterfall, these are like water bodies. And then you have groupings between different regions of like playing, like for example, basketball court, baseball field, and also some generic city locations like downtown, city hall, skyline, and penthouse. Next slide. Now, the next step is, once we have this taxonomy, can we associate that with movie clips? Or so why we are looking at movie clips? Because movie clips actually ensure that we can track the change in context. So we divide the movie clip, essentially a short movie segment, which is 2 minutes 30 seconds, into multiple shots. And we ask a human expert to look at the shot and see if there is any matching scene level in our taxonomy. So if there is a matching scene level, the shot is annotated in a multi-label fashion. If not, then we update the existing taxonomy with a matching scene level by taking into account wiki definitions. So in the end, we have like a multi-label shot level annotation for the clip. Next slide. Some of the examples here, here, for example, on the left one, we have, so these are consecutive shots in the same clip. So studio is the interior location here. So we also ask the human expert to mention whether it's interior or exterior. And so the right side, the next shot happens in a kitchen. And also, since it's a room, so we ask the annotator to mark like in a multi-level fashion, it's a room and a kitchen. Similarly, on the left part, we have a grove and walkway, which we can see once the person moves on the right side. And the next shot happens in a yard, which is a different location. So these are like a couple of examples that we obtained from our human in the loop annotation process. Next slide. So a couple of open questions regarding this curation process and also scaling up. So one thing I just wanted to mention was the usage of hierarchy. So we looked at representations to automatically discover hierarchy. Can we also enforce like structural and functional constraints and integrate that in learning framework? Like an example is classroom is structurally more similar to office than kitchen. A bus is functionally more similar to car, but they're structurally highly different. A similar thing is the temporal association part. So if a particular location is shown in short segments, can we have that mention, or can we temporarily associate that mentions of those locations across the duration of movie? And similarly, if a location has a lot of coverage and object occlusion, can we use the previous should we use the previous context to identify the scene, or should we just use the shot as an individual element? And last point is scaling up of the taxonomy update. So this is specifically to movies, but a lot of this taxonomy is also apply to media sources like advertisements and other digital shots. So can we have a scalable tagging process, which we can quickly use to update the taxonomy as well as associate with glyphs to create a large-scale data set. Next slide. So yeah, thank you for giving me an opportunity to present my work. Yeah.
Thanks, Iqbal. Great work. Let's open up for discussion for all three speakers, Ida, Ronak, and Iqbal. As before, if you have any questions, either add them in the chat, just raise your hand and ask it. Oh, Amruta, go for it. Amruta, you have a question? Oh, we can't hear you. No. You want to add it in the chat? One of us can read it out. In the meantime, I have a question from Sabi for Ronak. How did you extend the 5 basic emotions to decide on the final list of 25 emotions?
Hi, that's a good question. So we started off with the 6 basic emotions of Paul Ekman first, and then we started finding the synonymous words associated with those emotions, and found if there are images or instances where we could strictly differentiate between those affective states, then we would include it as an additional category. And therefore, we slowly grew our 6 from 6 to 26. And then actually we had more, but we had to cut down on few or merge few just because there were not enough instances where we could differentiate between 2 different emotion categories. So starting from 6 basic, we added more and more affective words. And you can see this reflected in the definitions of this each category. So for each category, we have this affective definitions like for affection, feeling loved, feeling close, like, feeling of love and things like that. So we would have this different affective states associated with each emotion, and then club them together to find 26 emotion categories. I hope that answers.
Thanks, Ronak. Amy?
Thanks. Yeah, either for Ronak or Digbale, some of the work that we've done in terms of kind of like image coding and news article coding has found it really challenging to code for sarcasm. So I was wondering if that was anything that either of you had come across. I know it wasn't on your list, Ronak, which I was kind of wondering if that was one of the reasons why. So yeah, just interested what you have.
Thanks. That's an interesting question. So for sarcasm, we could not find instances whether it could be defined as a feeling or be considered as something a person is feeling. Therefore, it was not easy or possible to include it as one of the emotion categories. So when you think about, I would say, when you think about sarcasm, it's something which is implied by language or through action about some comical situations rather than actual personal feelings. And therefore, although it is an important human action and behavior, it's not in the emotions categories, for us at least.
Thanks, Ronak. I had a quick question. I couldn't help but like pause on this image because a lot of emotion expressions can be temporal in nature. I'm not a skateboarder, but I couldn't quite figure out if the person was falling or if that was a very fancy move, because that would really affect how dominance would be labeled, right? So I'm curious, what do you think about like how much of some of these confusions could be from the limited context?
So I would say it could be also annotator biases as well. For example, when you look at this image, when you look at the person and you see that at this instant the person is not falling and might fall, but from his face it looks like maybe he's in control. So these kind of biases from the annotator also plays a role in capturing the exact perceived emotion here. So I would say that temporal nature also plays an important role, but because we are doing this recognition only on snapshots, or yeah, so.
Thanks, Ronak. I have a question from Amrita for Ida. Characterizing subjectivity in human-centric tasks is a difficult area. She enjoyed the talk. My question is, for a lot of tasks, for example, where we use mTurk annotations or so, we don't always control for who annotates what. Do you have thoughts on directions to extend this work where you have a large number of annotators and not enough annotations, or challenges you see that could make the task difficult or not feasible?
Yeah, thank you. I think it's like two different questions. And for the first part, that's right. We only used, we needed data sets that had like a mapping between annotators and their annotations to do this. And specifically because we thought our motivation was to think that the annotators are different and their annotations are somehow systematic based on their differences. We did use that, we did need that kind of annotations and that kind of data. So this approach cannot be applied when the data set only has like a number of annotations, but it's not specifically shown like which annotator has generated which item or which annotation. So that's why like in our first paper, we also like had some kind of recommendations for data curators to somehow make this mapping between annotators and their labels public, so that like the further for in modeling steps, we can use that kind of information. And for the second part, it's completely correct. Like when we have very few number of annotators from each annotations from each annotator, it's not possible to model their differences. One possible approach is to find out like how, what, for example, psychological concepts, for example, people with different moral values might have different approaches toward hate speech. So maybe we can group them based on this kind of specific differences. And in that case, we will have like a perspective, like a moral perspective with all the annotations from people with that perspective, and somehow model that perspective instead of the annotator themselves. So thank you for the question.
Thanks, Ida. Any other questions or comments for our speakers? Ronak, go for it.
Hi, Ida. I liked your talk a lot, and I think it was also very well, in the sequence that I talk about the data set and multiple annotators, and then you're talking about the annotator agreements. I have a question about, you talked about majority vote when there are multiple annotators, how you showed both the methods. You showed that you can take each annotator's labels independently and train on them, and then also take a majority vote of it. Let's say in my case, when we have 26 emotion categories and there are 5 different annotators, they have multiple labels, multiple emotions chosen. But when they choose a few of those emotions, they are also not choosing the remaining emotions, right? So do you consider this like not choosing particular emotion also part of your model building when you do this majority vote, as well as yeah? So does it affect, or is it important aspect? What are your thoughts on that?
Yeah, that's a very interesting question. We didn't dig that deeply into the emotion because we considered predicting each of the emotions as a different task. But yeah, that's a very important point, that the combination of the emotion, like not selecting an emotion, is also a behavior from an annotator. But I don't know if that is something that's captured in that emotion itself, but it's not captured in our approach. That's only considered each of the emotions and their labels. Thank you for this point.
Thank you.
Thanks, Ida. Any last questions? comments? All right, if not, let's thank the speakers again. And thank you all for the great discussion. All right, that brings us to the end of our talk. But before you go, let me hand it off to Cree for some closing remarks.
Hi, everyone. If you don't know me, I'm Cree Cole-McLaughlin. I lead a team at Google Research called Muse, which is Media Understanding for Social Exploration. We've been collaborating with Shri and Krishna and many others on the call for years on some of this work. And just to start off, I just wanted to thank everyone one more time for the amazing diversity of talks that we have. I think the most inspiring thing to me about these workshops is just the breadth of stuff that we end up discussing, everything from climate change to emotion data sets to Foucault's politics, and it really blows my mind, and I always have fun at these. So this is the third workshop in a series that we hosted. For a little bit of historical context, we were planning an in-person summit last summer in 2020. We were going to have a big event, and of course the pandemic threw a bit of a wrench in the works. But I think what has come out of it has been a really intriguing and inspiring series of workshops. And please go to the website and you can see some of the past events, artifacts from the past events if you weren't able to attend them. Unfortunately, we forgot to record the first one, but we have the second one, and we'll post the recording from this one, and we should get the slide decks up on the website as well. And so with that being said, I think the purpose or our sort of goal for these events has been to sort of bring together a community of researchers from very diverse backgrounds. So obviously we have a lot of interesting technical work going on here, but a lot of really thoughtful stuff from Wendy Chun's lab and Jed's lab at Colorado, and Sarah at the previous workshops shared some of the art she's doing at USC, which is pretty amazing as well. So the goal is to bring together this community and hopefully inspire and foster new collaboration. So I encourage all of you, if you're inspired by what you've heard today, to reach out to each other, kick off new projects, reach out to us, let us know what you're doing, stay in touch. On the website, there's sign up, so you can share that link with any other collaborators you have that might be interested in learning about future events. And next year we're planning on trying to these three workshops, we've sort of Shri and Krishna talked about the broad pillars, and we've been taking more of a breadth of perspectives in them, and we're hoping to start a series where we can kind of start to dive into more detail into specific topics. So we're hoping to kick off a seminar series next year that will be a virtual event, maybe happening more regularly with just one specific topic for each event. And then hopefully one day we'll all be able to meet up in person again too, and I'm really looking forward to that, and seeing everyone in person and talking about all these interesting things. So just thank you all again for everyone who presented, for everyone who attended. Thank you to Krishna for hosting this time, and just I just got to talk for 5 minutes. It's very nice on my end. Yeah, and a big thanks to Makaran for dialing in from India, and folks dialing in from Europe when it's super late. So let's just maybe give one more round of applause, and we'll close the event out, and hopefully we'll see everyone in the new year.
Thanks, Cree.
Thanks for organizing, Jen and Kathy. Thank you so much.
Oh yeah, good point, Shri. Thank you for the folks behind the scenes, Jen and Kathy, for making this all happen.
Yeah, Como, and all the organizers. Thank you.